To secure results-based climate finance under the UNFCCC framework, a nation must prove exactly what it lost. That requires submitting a rigorous historical emissions benchmark. For Cambodia, establishing this baseline required assessing over 181,000 square kilometers of territory across an 8-year reference period, from 2011 to 2018. The intuitive approach to solving a problem of this geographic scale is simple. Send satellites up, scan the terrain, and generate wall-to-wall land cover maps. Look at this official forest cover change map. The naive assumption is algorithms simply count pixels that shifted to brown, multiplying that area by carbon density. Distinct clusters of red pixels seem to clearly indicate boundaries where deforestation occurred. However, pixel counting carries a fatal flaw. Satellite optical sensors and automated classifications struggle to accurately distinguish complex layers within a dense tropical canopy. When analysts evaluate these raw satellite maps against physical field data, the overall map accuracy sits stubbornly at roughly 75%. In international climate finance, a 25% margin of map error translates directly into baseline uncertainty. If a nation cannot quantify its uncertainty, it is completely disqualified from receiving REDD+ funding. This created a central paradox for Cambodia's MRV technical team. They possessed highly detailed national maps, but the UNFCCC would mathematically reject those maps as final proof of deforested area. Relying on raw map classification creates unavoidable bias. A sensor misreading a shadow or seasonal change leads a nation to systematically overestimate its historical emissions. To bypass this accuracy ceiling, the team deployed a specific statistical methodology, the Stratified Area Estimator. The Stratified Area Estimator framework reconfigures the role of the map. It treats the satellite data not as a final record, but as an architectural guide for human sampling. Securing a carbon baseline is an exercise in statistical variance management. It requires a verified bridge between flawed orbital data and ground-level truth. Before any measurement of change can occur, the physical parameters of the baseline must be defined according to strict biological and spatial criteria. Cambodia established exact spatial requirements for its REDD+ forest definition: a minimum area of 0.5 hectares, a tree height of at least 5 meters, and a canopy cover exceeding 10. Imposing these strict definitions immediately narrows the scope of reference level, stripping vast tracts of agricultural land cover away from the accounting framework. Precise spatial boundaries ensure that standard agricultural rotation cannot be falsely claimed as either deforestation or reforestation. The full scope of REDD+ activities extends beyond deforestation. Countries can also claim carbon credits for the enhancement of forest carbon stocks, essentially reforestation. Cambodia's original baseline submission attempted to include these enhancement activities to maximize their total climate mitigation claims. However, the UNFCCC technical assessment revealed a major vulnerability. The geospatial identification of newly regenerating forests was drastically inaccurate. This side-by-side visualization shows the result. While deforestation tracking held up, the map accuracy for the enhancement activity was technically 0%, resulting in a 100.9% combined uncertainty. Under the UNFCCC's stepwise approach, submitting a single unverified dataset threatens the mathematical integrity of the entire submission. The technical team voluntarily stripped all reforestation data from the modified submission to salvage the credibility of their deforestation baseline. In international carbon accounting, unquantifiable uncertainty is a strict liability. Claiming less carbon impact with high precision is far more valuable than claiming massive impact with zero proof. Under the Stratified Area Estimator method, flawed pixel maps are demoted from their role as activity data. Instead, they function as pre-stratification tools. Looking at this map of expansion areas, we see the concept of pre-stratification in action. The map's rough color clusters tell human analysts exactly where to look closer. The baseline reference structure begins with this yellow grid, a systematic national forest inventory matrix. To find the actual deforestation, the team applied sample intensification. They placed tightened, specialized grids directly over the specific areas where the satellite predicted a high probability of change. These specialized grids included a 4-kilometer buffer zone for 2014 to 2016 changes, and a highly dense targeted grid for 2016 to 2018 changes, visible here as the dense clusters of purple and blue dots. The final scale of this verification operation produced a sprawling matrix of exactly 8,917 individual half-hectare sample plots flagged for manual review. By focusing analytical firepower directly on the exact borders of expected change, Cambodia reduces the margin of error without perfectly mapping the entire country. Teams manually analyzed 8,917 plots, utilizing high-resolution multi-temporal imagery to track degradation year by year until it was completely brown earth. Each plot was classified according to a strict hierarchy, manually overriding the satellite's initial guess with verified human truth. This raw truth is fed into the core mathematical engine, the Olofsson area estimator equations. The first critical variable is Wi, the map proportion, representing the total area initially classified as a specific forest type. The second critical variable is the reference count data, represented by Nij over Ni. This is the raw truth extracted directly from the 8,917 verified plots. The estimator actively corrects the biased map area. It multiplies Wi by the true proportion derived from the verified samples, resulting in p hat k, the estimated true area proportion. By processing data through equation 2, the team effectively replaces the biased map classification with the human verified reference classification. This calculation strips the inherent uncertainty out of the satellite pixel, producing a mathematically pure area estimate of actual deforestation. Even with 8,917 human verified plots, taking samples inherently produces its own statistical variance and potential error. To manage this, analysts build an error matrix. This cross-tabulates the map's original labels against the new verified truth to track every false positive and false negative. This diagram shows how the stratified area estimator utilizes Olofsson equation 3 and 4. These formulas ingest the error matrix and calculate the standard error. The output provides formal 95% confidence intervals, tightly bounding the final deforestation estimates. Within the SAE framework, the error matrix functions as an active mathematical tool used to quantify confidence. The final step is conversion, multiplying this highly accurate activity data by the specific emission factors, or carbon density, of each forest type. The ultimate output is a defensible benchmark of historical emissions, expressed in precise tons of CO2 equivalent per year. The hierarchy of truth established in this submission is strict. The math guides the sample grid, the grid dictates the area math, and the math defines the sovereign carbon baseline. The core result of Cambodia's modified submission is clear. In the modern verification landscape, rigorous statistical sampling outranks pure geospatial mapping every single time. For the RED+ framework to function, the data must satisfy the rigorous demands of international finance. In this environment, the only reliable path to funding is through verifiable mathematical precision.